Welcome to the Bohr Model. So, in the last video, I explained that we have a problem with Rutherford's atomic model, in that Rutherford's atomic model allows electrons to have any energies they want, but we don't see all energies able to be emitted from atoms. We only see certain energies that are allowed to be emitted, which means that only certain energies must be allowed for the electron to have. Because to change from one energy to another, it's got to emit that difference in energy. And so, if we only see certain energies being emitted, then only certain energies can be allowed. So this is where the Bohr model of the atom comes in. So in 1913, Niels Bohr develops the first quantum atomic model. So quantum means it's quantized. There's some fixed amount of stuff, some fixed amount of energy in this case. So in Bohr's model, the atom contains a very dense positively charged nucleus. That's just like Rutherford's model. But it also says the electrons in an atom move around the nucleus only in certain allowed circular orbits, or spherical orbits. So this, if they're only allowed to move in certain orbits, that then might explain those fixed energy differences that we see come out, those fixed line spectra that we see for different elements. So Bohr's model looks something like this, where we have a nucleus in the center. Now, it's not drawn to scale. And then we have various orbits around that, various rings. Here I have rings 1 through 4. These rings are not drawn to scale. They're just sort of thrown in there. And so what this now means is that we have an electron in the atom. So we've got our nucleus in the center. That has our positive charge to it. If we have our electron, maybe it's in the third ring. So maybe it's there. Well, that means that it's some distance away from the nucleus. And if it orbits the nucleus in our fixed circular path, it always has that same energy. It can be anywhere along that ring, and it's still the same distance from the nucleus, so it still has the same energy. But now, let's say that our electron moves and drops down to the second level. Well, as it drops down, now it's getting closer, which means it's losing energy. That energy has to go somewhere, so it gets emitted as a photon of light. And we can then detect that, well, that's a certain energy. If we move from 3 down to 2, or from 2 down to 1, or from 4 down to 2, or whatever, we have various possible combinations of our rings. Each ring has a certain energy associated with it, so the transitions from one ring to another have certain energies associated with them. This now finally explains the line spectra that we see for various elements. So, again, an electron can change orbits by absorbing or emitting light. So if we move down in orbit, then energy has to be emitted because the electron is losing energy as it gets closer to the nucleus. So we see a photon come out, that's this wavy line. On the other hand, if we have a photon come in, the electron can absorb that energy and move up, move farther out from the nucleus. Because remember, if the electron gains energy, in gaining energy it has to move out from the nucleus, because moving out from the nucleus moves the energy up, it moves it farther away. So we've given it some energy, it gets farther away from the object that's attracting it, the protons in the nucleus. So, the light that's emitted or absorbed corresponds to the energy levels. So the energy levels are these orbits, circular orbits, that the electron transitions between. Which means that the line spectrum is different for each element, because each element has different numbers of protons in the nucleus. Which means that the electron, or the energy of the electron at various distances, is different. So that means that these rings are at different places for each element. because each element has different numbers of protons in the nucleus. So those rings are in different places. So as we put more and more protons in the nucleus, those rings all get closer and closer in to the nucleus, because the electron is being attracted stronger and stronger to the nucleus. So, with electron transitions, so this is an electron moving from one energy level, one orbit, to another energy level, a different orbit. So, for the hydrogen atom, Bohr showed that the energy levels can be calculated using this equation. So, E, the energy of that energy level, is equal to minus 2.178 times 10 to the minus 18 joules times Z squared over N squared, where Z is the charge on the nucleus, which for hydrogen is positive 1, and N is an integer corresponding to the number of the energy level. So the first energy level has an N of 1, the second energy level out from the nucleus has an N of 2, the third energy level out from the nucleus has an N of 3, and so on. So again, so starting at 1 for the energy level closest to the nucleus, nearest the nucleus. So if we have an electron in energy level, say 3 for hydrogen, then Z is plus 1 for hydrogen, and N is 3. So we have plus 1 squared divided by 3 squared, so 1 over 9 times this quantity, this energy. And that would be the energy for our, for that energy level, that third energy level. Now, the energy of the electron that's infinitely far away from the hydrogen nucleus has basically an N value of infinite, which means that we have our energy value times the charge on the nucleus for hydrogen is plus 1 squared, divided by that N, which is here infinite, squared. So anything divided by infinity, infinity squared is still infinity, is 0. So this quantity becomes 0, which means the product here becomes 0. The energy is 0. So the energy of our electron that's infinitely far away from the nucleus is 0. But note that now any other energy, anything else that we put in here other than infinity, gives us a negative value, because we'll always have a positive charge on the nucleus. Even if it were negatively charged, it's still squared, which gives us a positive value. That N value is squared. N is always positive, but even if it wasn't, it would still be squared. So this quantity is always squared, and this quantity is always negative, which means unless our electron is infinitely far away, unless it's in the infinite energy level, if it's in any other energy level, that means that electron has a negative energy associated with it. Now, negative because it's falling down as it gets closer and closer to the nucleus. It's losing energy as it gets closer to the nucleus. So, let's go ahead and calculate the energy of a photon emitted when an electron falls from the fourth energy level down to the second energy level for hydrogen. So the energy of the fourth energy level is, again, our quantity, 2.178 times 10 to the minus 18th joules, times the Z value. Z for hydrogen, again, is the number of protons. Hydrogen has 1 proton, so the charge there on the nucleus is plus 1 squared. Divided by the energy level, we're looking at the fourth energy level, so 4 squared. So this quantity is 1 over 16 times our energy value, gives us minus 1.36 times 10 to the minus 19th joules. So that's the energy of the fourth energy level. And now let's look at the second energy level. Well, now we plug in a 2 here for N, and we square that, and that gives us minus 5.445 times 10 to the minus 19th joules. Now, you notice that this value, minus 5.445 times 10 to the minus 19, is a larger negative value. It's more negative than this value is, right? This is minus 1 times 10 to the minus 19, and this is minus 5 times 10 to the minus 19. So the second energy level is lower in energy than the fourth energy level. It's a more negative number. It's a more negative energy. So when we go from the fourth energy level down to the second, our electron is going to lose energy. If we go from the second up to the fourth, we have to put in energy to get our electron to go from this more negative to a less negative value. difference in energy then is the energy of the final state minus the energy of the initial state. So this symbol delta always means a change in whatever comes after it. So change in E, change in energy, it's always final state minus initial state. So the final state was the second energy level because we went from 4 down to 2. So the energy of our second energy level minus the energy of our first energy level. And that gives us now this difference of negative 4.04, negative 4.084 times 10 to the minus 19th joules. So that's the energy difference between the fourth energy level and the second energy level. So that's how much energy will be emitted. Now, we won't emit a negative energy. Right? The energy emitted with that photon is a positive value. It's positive 4.084 times 10 to the minus 19th joules. So again, the atom loses energy by emitting a photon. We know that it loses energy because the sign on our delta E was negative. That energy, that value, 4.084 times 10 to the minus 19th joules, is the energy that's emitted. And so that's why the atom is losing energy. The electron is losing energy. So the wavelength of that photon can then be calculated. So if we know the energy of the photon is equal to h nu, which is also equal to hc over lambda, we're going to use the hc over lambda because if we want to know the wavelength, we want lambda. If we want to know the frequency, we'd use this one with nu. So we can solve this equation for lambda. So lambda equals hc over the energy of the photon. H there, again, is Planck's constant. C is the speed of light. E is the energy of our photon, which we know now. So we can plug in our values. Plug in Planck's constant, 6.626 times 10 to the minus 34 joule seconds. Plug in the speed of light, 2.998 times 10 to the 8th meters per second. Divide by our energy, 4.084 times 10 to the minus 19th joules. And that gives us 4.864 times 10 to the minus 7 meters, which is small because it's 10 to the minus 7. That's 486.4 nanometers. Now that may be a value that seems familiar to you from the last video on the line spectrum of hydrogen. So this wavelength matches the green line in our hydrogen emission spectrum. So this is where that green line is coming from. It's from the transition from an electron in the fourth energy level down to the second. And so now, using our equation, well, the combination of this equation and this equation, now we can figure out where those lines in our hydrogen spectrum are coming from. We can finally figure out which energy transitions those are associated with. Is it from 4 to 2, 3 to 2, 4 to 1, and so on. Right? We can figure out which energy levels those transitions are for. And so now we have the combination of the evidence that we see with Bohr's model, and that gives us some evidence that Bohr is along the right track. Now, he's not totally right, but he gets us one significant step closer to what we currently think is true. So that was the Bohr model.